Thank you. Usually a speaker starts with thanking the organizers for inviting me to talk. I won't do it because I'm actually upset with the organizers who forced me to talk. Because I'm really talking instead of Bharat and Garajan who were supposed to talk. And then, you know, I knew he had problems with the visa, and it became more and more clear that he won't be able to come. And then Francesco, where are you, Francesco? So Francesco wrote to me, will you be willing to talk instead of Bharat? And you know, I wanted to help. Bharat was my student, I wanted to help. And only when I arrived there, I realized that Francesco is not speaking. He knows this subject by now better than me. So he really had to talk about that, because he did this. I'm going to talk about my work with Bharat and Glebsky and Monod, but later on, they applied the technology to other groups, and I really believe that Francesco now understands also our work better than me. So, you are now arrived. These are not the bad things about you. Okay, so anyway, I promise I will talk. So as I say, this is joint work with Lev Glebsky, Nicolas Monod, Bharat, Eran Garajan, and it's uniform stability for high-rank lattices. I will stress, let me just probably, I have to admit that I agreed because I had ready slides from a talk I gave some time ago, so probably for this conference, some of it is not needed, but still, let me go quickly over the basis. Let G be a semi-simple, but let's say it's a simple Lie group over a local field. Gamma a lattice, discrete subgroup of finite co-volume. We call it uniform if it's co-compact, or non-uniform if it's not compact. The rank of G is the rank of G over K. Now, as it's well known, there is usually a difference between groups of rank 1 and I rank. I rank means not very high, just greater or equal to, with respect to local rigidity, strong rigidity, super rigidity, congruence subgroup property. So usually the difference is illustrated fairly well by the difference between SL2Z and SLNZ. This is not always the case. You know, sometimes, you know, there are rank 1 groups satisfy super rigidity and things like that. This talk is about Ulam stability, which is another such a property. And let me say why I think of it as another such a property, that this Ulam stability is a kind of rigidity result. What is a typical rigidity result? Let's take super rigidity. Super rigidity says that if you start with a high rank lattice, it has some clear finite dimensional representations. Either representations coming from the Lie group, algebraic representations, and you restrict them to gamma. And these are fairly well understood. They are classified by the highest weights of the Lie algebra, etc., etc. And there are other representations coming from the finite quotients, right? The group is raised to all infinite, you get finite quotient. The super rigidity basically tells you that every representation is a kind of combination of these two. So like, there are clear examples, and every representation is only some of the clear representation. Now, what the Ulam stability is the statement that almost representations are also nearby representation. But warning, 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 the notion of almost representation I'm going to talk now, for most of my talk, is different than what has been done in this conference so far. And maybe this is the only lecture in this conference which is with this different notion, so I will be careful in a minute to, yeah, so let's define it very, very carefully because it's different than what we talked so far. So let gamma be a group, usually finitely generated group, and let Gothic G be a family of groups, each one with a bi-invariant metric Dn. Now, gamma is uniform or Ulam stable. People sometimes use uniform, sometimes they use Ulam. And if we don't want to decide between the two options, we just say that it's U stable. Gamma is U stable with respect to this family if for every epsilon greater than 0 there exists delta such that for every n and for every map, not homomorphism, every map from gamma to Gn such that Dn of phi gh comma phi g phi h is less than delta for every g in h. You see, we assume the same distance at the same bound. That's what makes it uniform. It's a stronger condition than what usually we call asymptotic homomorphism. This is that for every g and h, the distance between phi gh and phi g phi h is less than delta for every gh in gamma. So this is a stronger assumption that what was defined many times here as asymptotic homomorphism or almost homomorphism. And we want the conclusion also to be stronger, namely there exists an homomorphism psi such that the distance between phi n and psi of g and psi of g is less than epsilon for every g in gamma. So, you see, in short, every almost representation is just a small deformation of true representation. But this statement was said in this conference a number of times, but this is now in a different meaning. Okay? Maybe let's even stress it more. Warning, do not confuse it with the ordinary stability, which is equivalent to if phi n from gamma g, like if we have, now I'll give an equivalent definition to uniform stability, and I compare it to the ordinary stability. The ordinary stability says the following. That's the one we talk so far all the time. If phi n from gamma to gn, such that for every g and h, dn of phi n gh and phi n of g, phi n of h goes to 0, but the rate it goes to 0 depends on g and h, then there exists homomorphisms from gamma to gn such that the distance between phi and g and psi and g goes to 0. Again, the rate depends on g. On the other hand, with the uniform stability, everything is uniform. The assumption and the conclusion. Namely, what I defined in the previous slide of uniform stability is equivalent to if phi n of gamma from gamma to gn such that the supremum, not such that for every one it goes to 0, the supremum over all gh in gamma of dn phi n, oh, here it should be g times h, not g comma h, phi n of gh and phi n of g, phi n of h goes to 0, then there exists true homomorphism from gamma to gn such that the supremum over the distance is going to 0. Right? So I hope I made the warning clear enough. Okay. Now today we will talk about only about the group Gn, but with respect to a matrix Dn induced by a submultiplicative norm on M and C. We'll see a few examples. We take a submultiplicative norm on the n by n matrices. Submultiplicative means that the norm of A, B is at most the norm of A times the norm of B. And the distance is simply the distance between two unitary matrices now. A and B is simply the norm of A minus B. What are the examples we can work with? Is the operator norm, for example, right? Or the Frobenius norm. This is simply like the L2 norm of the matrix. Or the P-Schachter norm. The P-Schachter norm for every P greater or equal 1 less than infinity. Sometimes people consider the operator norm as the P equal infinity. This means the following, that the Pth norm, you take the absolute value of A. The absolute value of A is the following. You take a matrix A, and then you take here the star should be a little bit up. The square root of A star, A joint A. Now this is not positive definite, but non-negative definite, right? Or what is called. Right? This is a matrix that it's a normal operator, it's diagonalized, all the eigenvalues are real and greater or equal 0, so you can take square root of such a matrix, and we call it the absolute value of A. And the P-Schachten is you take A to the P, think of it as diagonal matrix, you basically take all the eigenvalues to the P, you take the trace, you sum them up, and then you take 1 over P, right? This is the P-Schachten norm. The case P equal 2 is simply the Frobenius norm. Okay, so all these are example of submultiplicative. A non-example is the Hilbert-Schmidt norm that we talked quite a bit about it here, that you take the L2 norm and you normalize it by 1 over n squared, and this 1 over n squared changed everything dramatically. It stopped to be submultiplicative, and we are lost. We don't know, by the way, also in the other problem, if we are lost, if the results are not true, or simply the methods that we are applying do not work. Okay. Now, what is the main results I want to present today? If we take now un and dn, and I only want the dn will be submultiplicative. I don't care which one of the P-Schachten. You can even take for every n a different type. It doesn't matter. Gamma lattice in a I rank simple Lie group over a local field, then gamma is Ulam stable, provided G satisfy a very ugly condition that we even couldn't find a good name for it, and we call it G of Q1, Q2. I will tell you what is G of Q1, Q2 toward the end of my talk, just that you think the condition is ugly, but still it is satisfied by most of the groups. Namely, first of all, it's satisfied always if K is an Archimedean field. It's also satisfied always if K is the complex number. With real groups, it's satisfied for most cases, but not for all. For example, for SLDR, it is satisfied if D greater or equal 3, but not for SL3R. As I said, for complex number, it's satisfied always, so in particular, it's satisfied for every I rank for all SLDC. But it's not in SL3R. So it's kind of a good group. Before we go into the game, let me tell you something. You see that this is the theorem about the lattice gamma. Now, I want to stress that when we know to prove it, we know to prove it for all lattices in a Lie group G. It's not like we can prove it for one lattice and we cannot prove it for another lattice. If we don't know, if the group does not satisfy, then we don't know to prove it for any lattice. Okay, so it's very short. It's going to be something depending on G and not on gamma. Okay, some history. Kashdan in 1982 proved that amenable groups are strongly Ulam stable with respect to the operator norm. What does it mean, strongly Ulam stable? They are Ulam stable even with respect to infinite dimensional unitary representation. Namely, you can take the definition, the same definition, and define it with respect to infinite dimensional Hilbert spaces. Namely, for every epsilon there exists delta, such that if you have an homomorphism to the unitary group, such that phi of GH blah 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 is less than delta, then you can find homomorphism, which is an epsilon distance. So you prove it for all of them. But in 2013, Burger, Ojava, and Tom proved that if gamma is any discrete group containing a free non-abelian subgroup, then gamma is not strongly Ulam stable. It's not strongly. The proof is interesting, but conceptually it's simple. Why? It is known, I think this was even proved before, I forgot now by whom, that free groups are not Ulam stable. You see right away the difference between stability in the sense we talk here most of the time and uniform stability. You remember in one of the talks somebody said, oh yeah, of course, free groups are stable, which is clear. Because in the way we do the usual stability, there is nothing to check. You check the relations, there are no relations. Free groups, that's a non-trivial. I mean, it's not so difficult, but it's a clever trick that free groups are not uniform stable, not Ulam stable. Now, what Burger, Java, and Tom did, they said, assume gamma contain a non-abelian free group of infinite index. They do, like you do induced representation, you can do also induced almost representation. You start with representations, with almost representations of the free group, which are not nearby representation. You induce them, then you will get infinite dimensional representations. The infinite dimensional representation now will be an almost representation, and you have to prove that it's still not nearby a representation. It's the same philosophy that Kashdan proved that groups, that the induction preserve, Kashdan property T, that it kind of preserve the distance. Now, okay, so we have this dichotomy. Amenable groups are Ulam stable. Groups containing the free group are not. They are strongly Ulam stable. Groups containing a non-abelian free group are not strongly Ulam stable. So it should ring a bell, right? It's like the von Neumann conjecture at the early days. Maybe some of the old people remember that von Neumann suggested that a group is non-amenable if and only if it contains a free group. This was disproved by Adian, I think, Olshansky. There are by now many examples of groups which are non-amenable without a free group. In this, I think this open problem, it seems like not known enough. I want to stress it here. Does strong Ulam stability characterize amenability? Some of us try to prove this in the positive direction, surprisingly, which would be kind of interesting, but we failed so far. I give you an hint, at least what I suggested. Some people, I cannot, I'm an old guy, but I suggest some young guy to try to do the Ojava Burger Tom idea. You see, they start with a free group and take the induction. But you know, we know these results of Gabriot, that every non-amenable group kind of measure theoretically contains a free group. Maybe one can start with this measure theoretically subgroup, which is not a real subgroup, and induce it up to take a non-risk. But this is, at this point, this is just a speculation, or if you want, a fantasy, to try to prove a characterization. Anyway, I think it's a lovely, lovely problem, and I want to take the opportunity to give it some, to make some propaganda for it. Okay, let's continue. The same paper, Burger, Java, and Tom, this is really the fundamental paper on all this Ulam stability. They also made the following observation, which is not difficult, but it's clever. If the embedding, you see, if you take H2 of gamma with coefficients R, but you take the bounded cohomology, if this kernel, there is always a map from the bounded cohomology to the ordinary cohomology. If the kernel is non-trivial, if this is not injective, then gamma does not have the Ulam stability. Basically, why? This is not so difficult to show that this kernel is a kind of an almost homomorphism to the real numbers. Almost homomorphism in some sense. I don't want to. Then you can take exponential of them, e to the I of this, and you get almost representation to the circle. So you really show that if this kernel is not, if it's not injective, already in dimension 1 you get almost homomorphisms to this. Now, I don't know if for some reason, I think you don't mention it explicitly, Andrea. I don't know if it was done parallel to you, but all lattices in rank 1 are known, it's known by now, I'm not sure if it was known when you wrote the paper, are known that this is not injective. For hyperbolic group is not injective, that probably was known at the time, but now it's also known that non-uniform lattices in rank 1 groups, this map is not injective. So here we are in a situation that at least we expect that the dichotomy between rank 1 and I rank is really strict. Namely, we know that all lattices in rank 1 are not Ulam stable, because it's known there that the map is not injective, and we expect that all lattices in I rank are Ulam stable. As I said, we know it only under some technical ugly condition on the group G. We'll come to it. Burger, Java, and Tom prove more. They really made the first step to prove for I rank. And they proved for SLDZ, or more generally for SLD of every ring of algebraic integers and even localized, that they are Ulam stable for d greater or equal to 3. But for that proof, they use in an essential way the fact that these groups, SLDZ or SLD, are boundedly generated. Let me recall that a group is called boundedly generated if it is a product of finitely many cyclic groups. Not direct product, but simply a product. You have C1, C2, up to CL. cyclic subgroups, and every element in the group can be written as one element from C1 times one element from C2 times. This is called boundedly generated. It's known for many non-uniform lattices in I-rank simple groups that they are boundedly generated, but it's not known yet for all. But people strongly believe that this is true for all non-uniform lattices. Some of us believe for many years that it's true for all lattices in I-rank, that they are boundedly generated. In fact, I wasted much of my time, and maybe I caused the community to waste much of the time trying to prove it, because Rapinchuk and I independently proved that this condition of bounded generation implies the congruent subgroup property, and we were hoping that this will be a way to prove the congruent subgroup property for I-rank lattices. It's known, the congruent subgroup property, for all non-uniform lattices, not we are boundedly generated, and it's known for some co-compact lattices. And we were hoping to this. Till a few years ago, Korvaja, Rapinchuk, Gren, and Janier surprised all of us. Actually, we were a little bit blind. You know, if you want very badly that something will be true, you close your eyes to think that it might be not true. So that's a good moral lesson to the young people. Don't believe in conjectures, even if the people who made the conjecture are, even if you have respect to them. Anyway, according to a recent results of Korvaja, Rapinchuk, Gren, and Zanier, co-compact lattices are never boundedly generated. They are never boundedly generated. You see, which means that the method of Burger, Java, and Tom probably can be extended, surely can be extended to many non-uniform lattices, probably can be extended to all non-uniform lattices once it will be proved that they are bounded generated, but it cannot work for co-compact lattices. Okay, let me just now say something about bounded cohomology. It's known that bounded cohomology of a amenable group is always zero. Now, over the years, it's proved that, you see, for rank 1 lattices, the second bounded cohomology is never zero. We even mentioned that the map from H2, you see, we mentioned that for rank 1 lattices, this map is never injective. In particular, this is not trivial, right? So it's never a bounded cohomology does not vanish for rank 1 lattices, but it's almost vanished for I-rank lattices. Burger and Monod prove that, okay, let's look at only modules where without a fixed point. The fixed point are going to cause us some troubles. Take on representations which with no fixed point, even on Banach spaces of sufficiently nice. Then Burger and Monod showed that it vanished for n equal 2. Burger and Shalom also prove it for n equal 2, but somehow for a more general V and a different proof, and then Monod prove it for every n. Now you see that we start to see a little bit of connection between.
No, but this is not true. Yeah, I think it's n below twice
What?
the rank. I think it's n below twice the rank.
Oh, you're right, for Monod. Oh, below by the 2 times rank,
Yeah.
right? Yeah, you're right. Yeah, I forgot. I'm sorry. Yeah. Yeah, sorry. You're right. Yeah. I have to edit. Now, Monod already in his ICM talk in 2000, he asked in a kind of a little vague way, is there a connection between Ulam stability and bounded cohomology? Well, now we understand the situation better, and the answer is yes, but. So let me explain. But before explaining this, even though I said I'm going to talk about the Ulam stability, I should stop for a few minutes and go back to the ordinary stability to illustrate somehow. Maybe this didn't come up in this conference so far so much, so I have to recall the connection between ordinary stability and cohomology, and H2. It was mentioned briefly in the previous talk and maybe in some other talk, but I want to stress it now in a slightly more technical way. Let Ln be the Lie algebra of the unitary group, and take any of the norms we discussed so far, but some multiplicative. And let L be the topological ultra product of this Ln. If you're comfortable with this ultra product, fine. If not, you can just think of it as you take the product and you divide it more or less by the direct sum, and you take, namely, sequences which converge to 0, you make them to be 0. The almost homomorphism field, now in the standard sense, not in the sense of Ulam, not in the uniform sense, if you have an almost homomorphism from gamma to Un, then you have an homomorphism to the ultra product of Un, or if you want, each one of the Un acts on Ln, on its Lie algebra, by the adjoint representation. Each one, the map from gamma to Un is only almost homomorphism. So the action of gamma on the Lie algebra via the adjoint representation of Un is only almost representation. But if you take ultra product of almost representation, topological ultra product of almost representations, you get a representation on the ultra product, on the topological ultra product. Okay. Now, what we prove at that paper, that if H2 of gamma with coefficients in this ultra product is 0, then phi n are close to homomorphisms. Okay, at that paper we study only Frobenius norm, only the L2 norm. What we observe that in this case L is a Hilbert space. In particular, if H2 of gamma is 0 on any action on any Hilbert space, then this almost representation, again, almost representation in the standard sense, are close to true homomorphism. So, if we work with the Frobenius norm and H2 gamma for every Hilbert space, then gamma is Frobenius stable. Okay. Later on, I think it was described in the lecture of Alon. It was extended by Izar Oppenheim and me for other LP, and recently also for L1 by Alon Dogon, Benny Bachner, and me. Anyway, what is now? I want to stop for a minute. Let's see. I made a picture. The real question is, what does H2 has to do with the whole subject. Why vanishing of H2 is relevant to this? I think it was not explained in this conference yet. So what does H2 have to do with stability? Here is the story. And now I'm talking about ordinary stability. The maps phi n from gamma to un give rise to true homomorphism. Why? You start with phi star. You start with gamma, which give you almost homomorphism to phi n, which give you almost to un. But if you take the product of them and you divide it by all the infinitesimal, you take the ultra product, then this is now phi star is a true homomorphism. Now, here is a trivial remark, but very important remark. Stability exactly means that this homomorphism can be lifted to an homomorphism psi from gamma to the direct product. Because what does it mean, homomorphism psi to a direct product? It really means bunch of homomorphism psi n for every n, right? And those psi n together, because of the commutativity of this diagram, must be nearby to the original field, right? So the stability is a lifting problem. This is the message. It's really a lifting problem after doing this little twist. Okay, we know that H2 is the machinery for lifting problem. This is classical by now. The problem here that the kernel from the product of un to this is such an ugly group, just think about it. It's a subgroup of the product containing the direct sum of the product, containing many others. It's a dense subgroup. It's such a bad subgroup, It's non-commutative in a very strong way. It's dense in the direct product of the un, and we cannot really handle it for lifting problem. When we have a good machinery for lifting problem, if the kernel is a billion, and then the key step is that even though the kernel K is very non-commutative, but here is not a difficult, this is maybe half a page, but you have to do it by yourself. If I will show you, you will never see it. If the norm is sum-multiplicative, then K be approximated by small abelian steps. And if you take the Frobenius, every such abelian step is Hilbert space. So you see, so we don't do the lift right away from ear to ear, but kind of we do it by steps. It's a little technical, but I don't have time for that. But basically, that's the idea. That's the reason why we need sum multiplicative. The sum multiplicative is needed in order to have this. Some people who are congruent subgroups lover like me may look at the following example. Take SL3Z. SL3Z and map it to SL3FP. The kernel is the first congruent subgroup, right? It's a very non-abelian group, right? It contains the free group. But if you take the congruent subgroup mod P, modulo the congruent subgroup mod P square, it is an abelian group. The congruent subgroup mod P square modulo the congruent subgroup P cube is also abelian. So you see, so even though the group altogether is very non-abelian, you can kind of cut it pieces for abelian pieces, and in a way you solve them step by step, and you take the limit, and then you solve the problem. Okay, that's basically the main idea of the paper of the Schifre, Glebsky, Andreasdom, and mine from a few years ago. Okay, now I have to confess that when Glebsky and I started to talk about the almost homomorphism in this Ulam stable, we noticed right away that if you apply the same machinery, you got a bounded cocycles. So it really well, we thought that we can do exactly the same machinery, but just do it with when you do the same, you can do the same strategy in principle, can work with the uniform stability, but the relevant cohomology is the bounded cohomology. And we told ourselves, okay, that's exactly the answer to Monod question. You remember Monod asked, is there a connection between the Ulam, the uniform stability, and bounded cohomology? If the bounded cohomology vanish, then we can do these steps in the others. I have to even confess further, we are among friends, right? I even gave a seminar at the university, luckily among friends. And I claimed that, yeah, we can do it. And then when we set up to write it, we saw that there was a very delicate mistake or gap. What we really have to consider are only what the logicians call internal cocycle, internal lifts. I'll say a little bit in a minute about that. Again, it's very simple after you see it, what it means and why bounded by itself is not the answer. Yeah. What we really have to do here is the following. We have to say the following. If gamma is Ulam G stable, if and only if every homomorphism phi which has an internal lift, not internal homomorphism lift, just internal lift. You see, if you take an homomorphism from, and now we are working with gamma star, the ultra power of gamma, we have homomorphism here. We don't have to solve the problem for every homomorphism. We only have to solve it for homomorphism here, which came from maps up here. Namely, it came from phi n, which are internal. That like for every n, you add a map going up. Only this is right. This is what we started with. Only those internal lift should be for every such phi which has an internal lift, we have to prove that it has an internal lift homomorphism. So we have to work in this ultra product, but only in internal objects. So I don't want to take the time to give the precise definition of what it means. Those who are familiar with ultra product and the language, it's not difficult, but you have to get a little bit used to this language. So now we could not really do it with the bounded cohomology, just right away to go to the shelf to take the results of Monod and Burger and Shalom and use it. What captured this lifting problem, again, only when the norm is sum-multiplicative, is a new cohomology theory that we have to develop. We have to develop a new cohomology theory, which we call it HNA, asymptotic cohomology. And this asymptotic cohomology is going over slowly and carefully on the internal objects inside the bounded cohomology. So this is a lot of effort. So when Glebsky and I discovered that, we thought we were going to write, before that, a 10 pages paper. Then at that time, Barat came to be a student of mine, and then we realized that it's much more difficult, that it will take much more time. And I knew Barat, and he has a lot of He's very, very talented, a lot of skill. He knows to write carefully and beautifully. I knew that if he will write a paper, there will not be more mistakes as we did in the first time. And eventually it was much more difficult. We call Nicolas Monod, who is the world expert probably now on bounded cohomology, for help. And it still took a few years and 80 pages, unfortunately. The paper is very long, so I will not bother you with all the details. I just give you a little bit of the taste why suddenly everything is becoming so complicated. If you want to read the 80 pages, you are very welcome. I don't recommend it. You know why? Because I think you should better try to find another proof. Or somehow do the asymptotic cohomology in a better way. Maybe you should read the paper in order to learn what not to do. But this asymptotic cohomology, actually, I should say, I said before Francesco walked in, that it's maybe somewhat useful. Maybe Francesco should explain why, because he already did some application of it with Bara to other groups, not just the iron lattices. So maybe it is a good theory, but it's not such an elegant thing that you can present on slides, you know. Okay, let's continue. So here is the main technical theorem. The main technical theorem says the following. After you define the asymptotic cohomology in a proper way, then the theorem is very similar to the theorem which I quoted before of the Shifre, Glebsky, Thom, and Mind, with the ordinary cohomology. If the asymptotic cohomology of gamma on the ultra product of the Lie algebra is 0, again, with respect to an action obtained from almost homomorphism in the uniform sense this time, then the vanishing of this cohomology implies a solution to the lifting problem, and the solution to the lifting problem means that the phi n are nearby to homomorphism. Namely, you have uniform stability. So this cohomology captures uniform stability just like the ordinary cohomology capture ordinary stability. Okay, now again, I want to mention some problems that we know basically to say nothing about. There is a canonical map from the asymptotic cohomology here to the bounded cohomology, but we don't know anything. You know, there are many works on the maps from the bounded cohomology to the ordinary cohomology. People started it as various meaning. We saw even at the beginning something about that, but here we know nothing. I even don't know, do we know, Francesco help me, do we know example that they are not equal? Maybe eventually they are equal, and then life will be, for example, then life will be fantastic. You see, if the internal cohomology give rise to the same thing as the bounded cohomology, that will be the most elegant proof, because then we have on a shelf the results of a Burger, Shalom, Monod, that the bounded cohomology vanish, and then we are in business. That would be the best. Okay, now the proof of Kashdan can be reproved. Like, it's not difficult to show that the asymptotic cohomology vanish for all amenable groups, just like the bounded cohomology vanish for amenable group. It's the same trick of averaging, etc. Okay, so this is the main theorem. So okay, so now we have to talk how we prove things like that for lattices. How we prove that this asymptotic cohomology is that. So here on one end it was simple, on the other end it was very complicated. Very complicated in the sense that not only that it took 80 pages, it took much more than 80 days, but it was simple in the sense that we took the proof of Monod and Shalom for the vanishing of H2, and we try to imitate it step by step for the asymptotic cohomology.
Is asymptotic cohomology only defined for higher rank lattices, or did you define it?
No, you can define it for every group. In fact, that's exactly what Francesco and Baraldi, they proved that the Thompson group are unstable. So that as a technique, it's a very good technique, because it really gives you stability out of vanishing of some cohomology. Okay, it's just that the compute this cohomology for lattices took a long time. I just want to illustrate what are the difficulties. And luckily, I tell you the truth, when we kind of hired Barat to the game, I thought that, okay, we learn a lot while doing this. Eventually, he became our leader, and he was the one who was that. And at several points, we felt like we are stuck, and he was the one who found the way. I just want to show you a little bit of the difficulties which come up. You see, in the usual bounded cohomology, you know, when people prove vanishing of bounded cohomology for high-rank lattices, they start with gamma lattice in G, and take a dual Banach space with gamma action, and they show that the bounded cohomology of B of gamma in V is the same as the bounded cohomology of G in W, when W is the induced representation. Right? This is a kind of the standard classical Shapiro lemma in this context. Okay, I mean, for finite groups, we maybe learn it in I don't know, in graduate school or in maybe even undergraduate. For locally compact with our measure, it's slightly more difficult, but it's a standard argument. But what do you do now? How do you prove? You see, we call it the cohomology of gamma and cohomology of G, but it's not really. It's cohomology of the ultra power of gamma inside the ultra power of G. The ultra power of G is not anymore locally compact group. The ultra power of gamma is not anymore a lattice, at least not in the ordinary sense. At some point, some logicians suggested that maybe there is a way to talk about this as lattices, and there is something called, you mentioned it today, Loeb, L-O-E-B measure or something like that. It might be that in logic or in model theory or something, there is a language to talk about that, but we didn't find this. And you really have to see the dilemma is, what does it mean L infinity of G star over gamma star? Think about it. You see that one can suggest several different definitions. What is L2? What does it mean, really? There is no hard measure on this space of. So you have to somehow look for the right definition that will work for you. So you know, we work by trial and error, and we did. So eventually we managed to prove. So you see, we took kind of the Shalom monod proof as our roadmap that we have to go through, and every step we try to imitate for the asymptotic cohomology instead of the bounded cohomology. For example, here is a major thing. For every dual Banach space, so we manage eventually to go to G instead of gamma. After the Shapiro lemma, the good thing is we forgot about gamma. Gamma is not relevant anymore for us. Okay? We just work with G. That's why what I stressed at the very beginning, if we know to do it, when we can do it for all lattices in G. If we don't know to do it, we don't know to do it for any lattice in G. Okay, so they prove that the cohomology lies only in the fixed point. Namely, the bounded cohomology of G is the same as the bounded cohomology when you restrict W to the G fixed point. That's a bounded. Now we want to have something like that for us. Well, Now you have to be even careful. What do you mean by fixed point? You say in an ultra product, we have to assume that W has no fixed point up to infinitesimal. I don't want to go to that. It will take me too much. So that's the best we can do, only under these assumptions. And then we managed to go a little bit further and say the following. We can do this if G satisfy this ugly condition that I tried to hide from you until the last slide. Only now I will tell you what is this ugly condition, GQ1, Q2. We even don't know, we even couldn't figure out a name for such an ugly property. G satisfy the condition GQ1, Q2 means that G has a two parabolic subgroups Q1 and Q2 satisfying the following two conditions. Q1 over intersection with Q2 contains a minimal parabolic subgroup, and together they generate the group. That's not difficult to achieve in all iron groups. But we need that, now notice, it's kind of interesting, we needed the bounded cohomology of Q1 with coefficients. Now the second bounded is 0, and the third bounded cohomology is Hausdorff. Not necessarily 0, but at least Hausdorff. Anyway, because of crazy reasons, this condition will give us what we want. Let me stress. This condition may be satisfied always. We don't know. Maybe, Francesco, you may know, and at least conjecturally may be satisfied always. So hopefully, at least this is not our fault. This is Francesco and his friends' fault. They should prove this, that eventually the third cohomology is always Hausdorff. But this is the serious issue, because the second cohomology with coefficient with R is not always 0. Take SL3R. You say if you take SL3R, there are not too many options for parabolic subgroups whose intersection is the Borel and generate the group. You can take basically the one parabolic and the other parabolic. These parabolic groups modulo their unipotent are just SL2R. But we know that for SL2R, the bounded cohomology does not vanish. It's related to the fact that for a free group, the bounded cohomology, for lattices there, it's never vanished. So we cannot recover SL3R. SL3R, we cannot do it. Basically, we can go over the list of real simple Lie groups and check this condition, check what is known in the literature about that, and check can we find such a that. And so as I said, many groups satisfied it, even most of them, but our result is not complete. We tried, at some point we gave up, and we decided to leave it for the next generation. Thank you.
Any questions for Alex?
Just to be sure that I understood, you expect that the second condition maybe you can remove.
The second part of the second condition, not the first.
Only the second.
The second part, I hope that eventually the bounded cohomology people will prove that it's always Hausdorff. I think even since we wrote the paper, there are a few more cases for which it was proved. But the first, this is simply not true. You see, if you take Qi to be a parabolic subgroup in SL3R, not Borel, which is amenable, but above it, there's only one basically, then modulo de Borel, modulo the unipotent radical is SL2R. In SL2R, H2 of it is not 0. So there is no way this is going to work for general group. Even for SL3R it's not. For SL4 it's okay. So as I said, for SLDR, where D greater or equal 4, We know that the theorem is old. There are a few other cases like that we went over the list of all the diagrams for Lie groups, and we could say which one of them this condition is satisfied. It's for many of them, but also there are infinitely many of them for which it does not. So it's not only SL3R. SL3R is easy to show.
So you didn't really define the asymptotic cohomology, but
Yeah.
I think I have got some idea. But so my question is, can you do this for ordinary cohomology as well formally, but then it's the same as so it doesn't change anything? Is that what
You mean
happens?
to do? You don't have to, because well, you want to do it for the cohomology, or you want to do it for stability? The ordinary
For stability,
stability
the issue does
is
not appear.
only about the generators. It's not an infinite object. You see, you take the generators and you can say it's kind of, you just look at the finitely many generators. In some sense, you can think of a map in the ordinary stability, just a map from the generators to something, so that the relations are almost satisfied. It's not a map from an infinite object. So this, when you go to the ultra product, you can really talk about cohomology of G, of gamma. Now we have to really talk about cohomology of gamma star.
Yes.
Even though I call it cohomology of gamma.
And so if you do it for ordinary cohomology, it wouldn't give you anything new. It's just the same. If you do it formally.
Never thought about it. I don't know. I must tell you, the way we did it here, we kind of went according to the needs. You know, suddenly we realized we need this, and the asymptotic cohomology is not a difficult definition, but it's kind of, it's a reverse engineering. You know, we wanted the theorem to be true, that if the asymptotic cohomology vanish, then you get uniform stability. So, and we realized that what we need is to solve internal cocycles by internal, that they are co-boundaries of internal cochain. You have to be only with internal and not with all. If somebody will come up, that's what I hope. If one day somebody, Francesco for example, will come and say that asymptotic cohomology is always equal to the bounded, we don't know that it's really different. But that's what we needed for the proof.
Any other questions for Alex? Let's thank him again.